Alexander Boxing. Eric, professor of astronomy at Cambridge University in the United Kingdom. He is a fellow of the Royal Society, which is the UK Academy of Sciences, and former chairman of the UK National Commission for UNESCO. Eric?
I'm going to begin by pointing out, as all of you know better than I do, how important Islamic history in science has been. And am I speaking to the right? Okay. It began with mathematics, and without mathematics there's no science. It was invented in Islamic countries. You don't have to read it all, but you know this very well. And not only mathematics, but what it leads to. Astronomy also came about through work in Islamic countries, with facilities, but with thinking, with understanding of what is observed, and it presented the foundation for European science and European astronomy in particular, and certainly the means of calculating things in science through the mathematics. So there's a basic foundation from Islamic science that we all now benefit from, and it's been referred to in history by famous astronomers and famous scientists. So building on that, I can give you a lecture. And this is about astronomy which is modern. But of course it requires all of the history and the development that there's been in the past. But here's a picture of the sun, and of course what we have with it. And when you look at the sun a bit more closely, often you'll see it yourself, sunspots. Now, the sun seems to be stable and bright and so on, but if you look in detail, the sunspots are darker, and there's also structure, which is due to convection, and slightly cooler regions which are darker and brighter regions which are hotter on the sun, and this is active all the time. And if you look at the hot part of the sun, which is outside the white globe you see, up to 2 million degrees, it's extremely energetic and not at all like you imagine. And this is what produces the solar storms we see, and particles come from the sun. So the sun is extremely active. It seems to be the same every day, but there's a lot going on. There's a lot going on inside too. Now here's again in our solar system, the Earth and the Moon. That's the Moon. And if you look at the rest of it, there's the planets. Mercury, Venus, Earth, Mars, Jupiter, enormous planets here. These are mostly gas. This was called a planet, Pluto. It's no longer, it's an asteroid. It's arguable what you would call it. It's got a moon of its own as well. Jupiter has 4 moons, big ones, seen by Galileo first. And we visited these with spacecraft. We've visited Mars with spacecraft, but most of the universe we can't do that to. The nearest galaxy to us is 2.5 million light years away. So what we have to do in astronomy is to try and understand the universe, is to use the light or electromagnetic radiation, which is all of the concept of light, and the observed laws of physics to gain understanding. We need the combination. And it's not a matter of guessing, there's evidence for it all. So we take light, which we could call light in general, that's our own light that we can see, gamma rays to radio, and short wavelengths, that is, to longer wavelengths, and you see hot gas, very energetic objects, black holes, stars in general, cold gas. All of this is now not perfected, because we never will be perfect, but we've taken it to a very high level. And the simplest sort of light source is just a hot body. And here's one where the visible range that we can see peaks. And of course, this is the spectrum of the sun. We've grown to accommodate to this. And the wavelengths that one sees, short for gamma, here are ours, to radio waves here, microwaves in your oven, but also in radio astronomy. So this is what we see in the simplest of objects, just hot things. But if one takes what one generally sees in the sky, you have the hot things like this. By the way, this is a spectrograph, very simple, just a prism. I'll show you a more complex one later. And with this you can spread the light out like this into its colors. But if one looks at hot gas, you see very small regions of light. And if you look at cold gas with this hot object behind it, the light coming through, the same lines are dark. Now this is due to the atomic nature of matter. So a nucleus has electrons around it. This is a very simple model, the Bohr model of the atom. And transitions in the positions of the electrons can be changed by absorbing light when they jump up to a higher energy, and then they fall down again. And when they fall down, they emit the light that represents the energy difference. So you see the bright lines. This particular one is hydrogen, and there's very specific lines from hydrogen. If one looks at other elements, lithium, sodium, potassium, rubidium, and so on, mercury, neon, then each one has its own signature. And this enables us to see in the whole universe what elements there are wherever they are. And also how energetic is the material from which this light comes, because you can see the balance of these lines changing when they jump up and down and so on. And therefore most of our evidence from our telescopes comes not from the images, which are fantastic, but from the way we analyze the light. Now, the picture of electrons in an atom is actually not true. It's a model. What we use in practice is quantum mechanics, and a photon, a particle of light, isn't in a particular position, it's a probability for it. And the atom then doesn't look like it's got electrons going around, but sort of clouds. And we work in quantum mechanics for all our real work. But I must tell you that nobody understands quantum mechanics. What we know what to do with it is how to use it, but the mind cannot grasp it. For example, one can work in 10 dimensions, impossible to realize. But even so, one can manipulate data and physical evidence in the mathematics without understanding what